Okay, let's take a look at a few examples of solving inequalities that involve an absolute value. Example number 1. Suppose we wish to solve the absolute value of x minus 3 is less than 5. Well, there's actually a couple different ways we could proceed here, one possibly easier than the other. Notice we have an absolute value of a difference. When you see the absolute value of a difference, like the absolute value of a minus b, and supposing that a and b show up on the number line somewhere like this, or possibly in reverse order, it actually doesn't matter. This value right here is simply the distance between those two values on the number line. Okay, so if that's equal to d, then this would also equal d. So with this in mind, when we see the absolute value of x minus 3 here, we can interpret that as the distance between 3 and any value of x that solves this inequality. So let's draw our number line. There's 3. Now if I have any solution to this inequality called x, then the distance between x and 3 had better be less than 5. That means I'm staying fairly close to 3, right? I can go no more than 5 units forward from 3. So that would mean that we would have all of these values here are solutions for x, except for the guy here at the end, which would be 3 plus 5, or 8. And I can go no more than 5 units backwards from 3. So all of these guys here, they don't go any more than 5 units backwards from 3. They're all solutions as well. But if I go back exactly 5 units, I see that we end up at -2. And because of this strict inequality, that one's not going to be a solution. But everything in between -2 and 8 is certainly a solution, including 3 itself, of course, because 3 minus 3 is 0. We're done. Everything from -2 to 8 are reasonable values for x that make this true. Okay, that's very fast, nice and clean. Now there's another way we can go as well. We can use the property of absolute value that essentially when you are taking the absolute value of something, if whatever is inside of it is positive, then the absolute value doesn't do anything to it. If whatever is inside the absolute value is negative, then the effect of the absolute value is to change the sign. Of course, we can change signs in other ways as well. For example, you can take a value and multiply it by -1. That will do the same thing. So another way we can go, if I started with this, is to consider those two cases separately. Either what's inside the absolute value is positive. Of course, that's the same thing as saying it's greater than 0. And actually, we can lump in 0 itself in this particular situation. Either what's inside the absolute value is positive and or 0, in which case the absolute values have no effect, which means I can write x minus 3 is less than 5. Or whatever was inside the absolute values was negative, so x minus 3 is strictly less than 0, and the effect of the absolute value is to simply change the sign of x minus 3, which we said we could do by multiplying by a -1. So negative times the quantity x minus 3, notice those are not absolute value marks anymore, is less than 5. So this one little statement is equivalent to all of this. Okay? Now let's take each one of these possibilities in turn. If the top one is the case that we're in, well, let's write it more simply. X minus 3 is greater than or equal to 0. That's the same thing as x is greater than or equal to 3, right? Just adding 3 to both sides. And over here as well, we can write things more simply. Add 3 to both sides here. This would give us x is strictly less than 8. Or what happens down here if we're in this case? Well, Add 3 to both sides again. X is less than 3. And over here, well, we got a couple things going on. To isolate the x on one side so we get something nice that looks like this, let's negate both sides. That is, multiply both sides by -1. That's going to flip the inequality symbol. And we're going to get a -5 over here. But then we're immediately going to add 3 to that. So -5 plus 3 is -2, and we're left with x on this side. Okay? So all of this can be written more simply as all of this. Now, let's look at the number line and these two cases. So here's 3, here's 8, here's -2. You can either be bigger than or equal to 3 and strictly less than 8. Let's see, that puts us right here. Or we could consider points that are less than 3, so over here, and greater than, strictly greater than, -2. So I don't want to include -2, and I can go all the way up to, but not include 3. Of course, 3 is included in the piece above. And here again, we have everything from -2 to 8. We're done. That's our solution set. Okay? A little more work when you can't take advantage of that distance interpretation, but this is a nice general method as well. Okay, let's look at a second example. Number 2. The absolute value of 3 plus 5x is greater than or equal to 6. Okay, let's try the second technique first this time. So again, we think about the different possibilities here for the absolute value. Either what's inside of it is positive, in which case the absolute value has no effect, or what's inside of it is negative, in which case the absolute value simply changes its sign, effectively multiplying by -1. So considering those two possibilities, either what's inside is positive or 0, right? Just like before, we can consider that case as well. In both of those scenarios, then the effect of the absolute value is no effect at all. We can simply drop the absolute values and say 3 plus 5x is greater than or equal to 6. Or we could be in the scenario where the absolute value is actually doing something, where the inside is a negative value, which we can write this way. 3 plus 5x is strictly less than 0. And again, in that case, the absolute value is merely going to change the sign of its contents. And so we could accomplish that in another way, a way not using absolute value symbols, by multiplying by -1. So negative times the quantity, 3 plus 5x, is going to be greater than or equal to 6. Okay, so we kind of pulled that apart. Now, these cases can be simplified, of course. In the first case, let's see, to solve for x, we would subtract 3 from both sides and then divide by 5. Wouldn't that give us x is greater than or equal to -3 from the subtraction and then divided by 5? And likewise over here, to isolate the x, subtract 3 from both sides. It's going to put a 3 here and then divide by 5. So we have x is greater than or equal to +3, remember, from 6 minus 3, divided by 5. Or we could be in the bottom scenario. Again, solving for x here, take the 3 to the other side, divide by 5, just like we did before. We still end up with a -3/5 on the right. But of course, our inequality symbol is a little different. And then this one, you actually have several different things going on here. Let's maybe do it off to the side, just so we don't lose track. If we have this, then we could negate both sides. That's going to flip the inequality symbol. We could subtract 3 from both sides to get -9 on the right, and then finally divide both sides by 5. So we get negative 9/5, and that's what we would put here. Okay, so all of that is equivalent to what we have here, and much more briefly, what we have here. But at this stage of the game, we can start looking at our number line. Let's see, where are all these things at? We've got a negative 3/5. Let's identify where that is. We have a positive 3/5. Maybe that's over here. Looks like 6/5 away. And we have a negative 9/5, which would be 6/5 the other direction. And we can see that we have one case where x is bigger than or equal to negative 3/5, and it's bigger than or equal to 3/5. If both of those things have to be true, doesn't that just mean this is true? That you're either on this or above it? Okay, so that's one scenario. The other scenario, you're less than negative 3/5, so we're over here somewhere to the left of this guy, and you're less than or equal to negative 9/5. So you're over here somewhere. Again, the overlap between those two, isn't that just to the left of negative 9/5? Or possibly on negative 9/5? Okay, and so that's our solution set. If you want to write it in interval notation, we have this interval here from negative infinity up to negative 9/5. So negative infinity up to negative 9/5. We're, of course, never including negative infinity. It's not even a number. We do include negative 9/5, so we'll use a bracket there. We have another interval over here that goes from 3/5 to infinity. Again, we can never include infinity. It's not a number. We do want to include 3/5, and that traces back to this non-strict inequality for both of those brackets. So those are the two intervals. We want to allow for the possibility that x could be in either one of them, either this interval or that interval, and so we join these two things together with a union operator. And so that is our solution in interval notation. Okay. Of course, you might be asking yourself the question, could we use a distance interpretation to solve this? Let's try. If we're going to use this interpretation of absolute value as a distance along the number line to solve this particular inequality, let's remind ourselves of how this played out last time. Previously, we had the absolute value of x minus 3 is less than 5, and we interpreted this as the distance between x and 3. But notice the form here. First off, we have an x, not a 5x, just an x, because we want to talk about the distance to some value for x. And second, we had a difference, not a sum. So we need to address both of those things. We need to get this, as best we can, into a form that looks more like this. Well, as far as getting the x there in the front, certainly swapping the order of those two terms inside the absolute value doesn't make a lick of difference, so we're free to do that. To get rid of the 5, what if we divided everything by 5? That would work in a linear inequality without absolute values. Works in linear equations. How about here too? Certainly that works. Okay, if we divide by 5 on both sides, that's the same as dividing by the absolute value of 5, which means since the quotient of two absolute values is the absolute value of the quotient, we can write it like this, and then breaking this into two pieces, we have 5x over 5, or just x, plus 3 over 5. In absolute values still is greater than or equal to 6/5. So we have the x that we want. Now let's focus on getting a minus here. So we're taking the absolute value of a difference. But that's easy enough. Look, can't we just rewrite this as x minus negative 3/5? So those negatives cancel out and give me the positive that I know I have there. So now I have this as an absolute value of a difference, and I can interpret then this as the distance between some value of x that solves this inequality and negative 3/5. So let's locate negative 3/5 on our number line. This says the distance between some value of x that solves this inequality and negative 3/5 is bigger than 6/5. So I have to go out at least 6/5 to either the right or the left to get to values of x that make this true. Let's see, if I add 6/5 to the right, that's going to put me at positive 3/5. That one I want to include, right? We have a non-strict inequality here. And anything to its right, right? Anything bigger than the 6/5 being added to negative 3/5. Likewise, over here, if I subtract 6/5, that's going to take me down to negative 9/5. If I subtract even more than 6/5, that takes me farther to the left. And so I shade those in as possible values of x that work. And here again, because of the non-strict inequality, I want to shade in negative 9/5 as well. And so just as before, we have this solution set that goes from negative infinity up to negative 9/5. It includes that one, never includes negative infinity, or from 3/5 up to infinity. Never include infinity, but we want to include 3/5 this time. It's filled in, and we want to be able to take x from either interval, and so we link them together with a union operator. So that is our answer. Again,